Welcome to Intro2Astro 2024.
Hi, and welcome to another module of Intro2Astro. I am Maria Vincent from the Institute for Astronomy in Hawaii. Let's dive into a little bit of instrumentation and look at a technique that has revolutionized imaging in astronomy. The title slide features a photograph of the two Keck telescopes at the summit of Mauna Kea, a large dormant shield volcano on Big Island, Hawaii. There are a few aspects of this slide that may seem foreign to you, which I'll talk about during the course of this presentation. What's AO? What are the two yellow beams coming out of the telescope domes? And why do we have telescopes on a volcano? So to start, let's ponder on a simple question that motivates the technique described in the rest of this talk. Why do stars twinkle? This little animation explains that. Starlight goes through several layers of atmosphere and it undergoes refraction at each layer. In addition to that, its propagation is affected by the winds in the atmosphere and by areas with different temperatures and densities. This is broadly referred to as turbulence. So, a combination. Our atmosphere is not exactly homogeneous. You can imagine air as being broken into different parcels or cells. These cells have different temperatures and densities, and they interact with each other. As a result, the image of our target seems to be blurred or smeared or even scintillating. This is called atmospheric seeing and is quantified as the size of the target as imaged by the telescope before any correction is applied. This cartoon is here just to reiterate the complicated physics of turbulence in a very simple fashion. The incoming light is originally a set of plane waves, which then pass through patches of air represented by the red clumps. And out comes a distorted wavefront. And this happens over several layers of atmosphere over a long distance before reaching the ground. To put this in more optical terms, each of the air packets or cells act like little lenses, and the starlight has to propagate through multiple lenses before reaching the telescope. Ideally, if the light rays are parallel, the telescope's optical system can focus those rays to a point. But in this case, they're not parallel. The distorted wavefront thus creates a problem now because the light rays cannot be focused to a point and we thus cannot get a sharp image. Way of dealing with turbulence is to observe from a higher elevation. That's one reason why astronomers choose to have telescopes on summits of mountain, or in this picture, a dormant volcano in Hawaii, which on a map looks like a spot in the middle of nowhere. Mauna Kea is an excellent location for several other reasons as well, but just the elevation of 4,205 meters, which is almost 14,000 feet, gives an advantage to overcome some amount of turbulence, as most of the issue with the mixing of air parcels occurs at lower altitudes. To combat turbulence more technically, we have a very elegant technique called adaptive optics, or AO for short. With AO, we can get sharper images of fainter objects and study them in greater detail. On a grand scale, the AO workflow is quite simple. The objective is to correct the distortions in the incoming wavefront or the incoming waves of light. Incoming wavefront hits and bounces off a deformable mirror, which is a mirror that can change its shape. The wavefront is split into two parts by the beam splitter, right here. One part of the wave goes to the detector, the other part to the wavefront sensor. A wavefront sensor measures the distortions in the wavefront, and accordingly, the mirror can deform or change its shape to correct for these distortions. In the end, the corrected wavefront enters the detector, which gives a sharper image, as you see on the little computer screen. Right there. Now let's take a look at some before and after correction images to get a better sense of how helpful adaptive optics is. Look at this blob. It's big and fuzzy at the start, and it would have seemed like a single large star. But thanks to AO, we can achieve a higher angular resolution than what's determined by seeing. In fact, it's going to be close to the actual resolution of the telescope itself. And we see that it's not one star, but it's actually a binary right here, and there's a third star off to the top right. This is a classic animation to demonstrate how useful AO is. Turning on AO, we can actually see the individual stars around the galactic centers. This is especially important as the presence of a supermassive black hole at the center of the Milky Way was determined through years of observing and charting the orbits of nearby stars. Without AO, that's just two bright spots on a pear-shaped blob, but the enhanced details after using adaptive optics reveal a better image of Neptune. This is a simple schematic representing the main components of an adaptive optics system. Let's take a closer look at the two of the main parts. The deformable mirror is what determines the shape of the wavefront sent to the science detector and wavefront sensor. It comes in different types. Each type has its own kind of mechanism that allows for the mirror's shape to be changed based on what the incoming wavefront looks like. So in this animation, you can see the difference between the distorted and corrected wavefront on the left and the right respectively, and how that shows up on the detector. Once AO correction is applied by changing the shape of the mirror, as we see in the center, the light from around the central source is concentrated in the core of what we call a point spread function, which looks like a Gaussian. The intensity increases in the core, which is the central part of the curve, and decreases in the halo, the outer part of the curve. Thus, we get a sharp point-like image as seen on the right. These are just a few types of deformable mirrors. The segmented mirrors are made of separate segments with small gaps and are controlled by actuators, which are little piston-like devices whose motion helps control the shape of the mirror. Bimorph DMs have piezoelectric wafers bonded together with an array of electrodes between them. The front surface acts as a mirror. What you see in this image is the wiring on the back. A continuous phase sheet DM has actuators that modify the shape of the DM, but instead of being broken into segments, is just a single thin glass sheet, and hence the name continuous phase sheet. Microelectromechanical systems, or MEMs for short, are a new innovation that's quite unconventional and also very small as a penny, in fact. They are fabricated using microfabrication methods used for integrated circuit chips. Their small size and potential for mass manufacturing make them potentially inexpensive. Now let's go to wavefront sensors. Just as the name suggests, it senses the wavefront, that is, measuring the aberration or how much deviated the incoming wavefront is from being perfect. Different wavefront sensors have their own working principles to measure this aberration. Two common types, at least the ones I have come across for my work, are the Shack-Hartman and the pyramid wavefront sensor. And the Shack-Hartman sensor, which you see on the right, we have a collection of small lenses called a lenslet array. Each lenslet takes a part of the light coming from the pupil where all the light enters and forms the corresponding image on the same detector. On the top, you see the case of a perfect wavefront where all the images formed by the lenslets come together in a neat grid pattern on the detector. As soon as the wavefront is distorted, as you see in the bottom image, you see that the images are formed far away from the nominal positions. Sometimes close, but in the outer cases, you can see it's quite far. The deviation in the X and Y direction corresponds to the wavefront slopes, which is communicated to the DM, and it assumes the needed shape. A pyramid wavefront sensor, as the name suggests, involves a pyramid, and that's what you see below here. The light enters from the top vertex of a transparent pyramid, which splits the wavefront into 4 beams, each producing an image of the pupil. For a distorted wavefront, the intensity distribution among the pupils will change. The local wavefront gradients can be obtained by recording the distribution of intensity in the pupil images. The wavefront aberrations can be evaluated from the estimated wavefront gradients. To apply the wavefront correction we've talked about so far, the wavefront gradient or the distorted wavefront needs to be measured somehow. There should be some sort of a benchmark to measure the turbulence. So, what is that? We call that a guide star. As written here, it is essentially a reference point to measure the distortions in the incoming wavefront and apply the appropriate shape to the DM. It comes in two types, and you've actually already seen one type. Remember the laser beams from the title slide? That's for a guide star. We can thus create an artificial guide star using a laser beacon to illuminate a spot in the atmosphere. Or we can use a bright star close to a target if such a star is present. If you recollect the AO system schematic, it's a lot of parts. All of that has to fit somewhere in the larger telescope hardware, right? Typically, it is fitted behind the main telescope mirror. The exact position depends on the other parts and the mount setup of the telescope. The image on the left is from the Lake Observatory on the summit of Mount Hamilton in California, and the arrow points to where the AO setup is. On the right is a schematic of the Subaru telescope in Mauna Kea, and here is where the older AO system resides. This talk would be incomplete for me if I don't mention how I use AO for my research. My work is centered around an application of AO to directly image exoplanets and circumstellar disks. This is called high contrast imaging. The objective is to get images of faint objects at close angular separations from the host star, and hence requires high contrast as well as high resolution. It is achieved through the confluence of three techniques. One is AO, as we discussed earlier, and the other is extreme adaptive optics, which is a more advanced version. Here, the wavefront corrections happens at a much higher speed, and the DM can assume more complicated shapes due to having way more actuators. The second is coronography. Where using special devices, we can control the diffraction inside the telescope and mask out direct starlight, hence improving the contrast of our faint target. And finally, we need a way to disentangle the light from our target from that of the host star, which can usually manifest as speckles. For this, we need post-processing techniques. There's a lot more to discuss here, and that's another talk of its own. On the right is the illustration of high contrast imaging. It's a sequence of images on the HR 8799 planetary system captured using the Keck telescope over a span of 10 years. The central part, which is marked by a little yellow star, is where the host star is supposed to be, but we've blocked it out through coronography. And you can see four little planets going around that center. AO has other applications as well. It's not just exclusive to astronomy. One application is in vision science, where we use it in surveillance cameras to provide real-time and long-distance imaging. It's also used by ophthalmologists to image the retina without aberrations to get a clear picture of the human eye. It is used in microscopes to correct aberration that comes from the samples, as well as to get images with deeper focus without having to move the objective of the microscope closer to the sample. Another application is free space optical communications, which is based on the transmission of light through an area of free space to transmit data. This uses horizontally propagating waves between optic components. This often leads to a high degree of turbulence and distortion of the light waves in the free space region. Adaptive optics can correct these disturbances and improve the transmission of data over long distances. The use of AO can also provide an increase in the speed of the telecommunication system. Finally, the biggest application area of AO is perhaps lasers. Some common applications that utilize lasers with AO include atomic trapping, understanding light matter interactions at the atomic level, laser cutting, quantum computing, and free-form metrology. Many of these laser applications are possible because AO enables the laser's beam shape and size to be controlled, which makes it more accurate, especially in the cutting and manufacturing of materials. I hope you were able to learn a lot about AO over here, and if you have any questions, you can reach me through Discord or Piazza. Thank you for your attention.
All right, folks. Any questions on adaptive optics? Just giving you a flavor of what instrumentation is all about. Forming good images on the sky, removing starlight so you can see exoplanet, light from the exoplanet. Okay, there's no more question. Let's move on to JWST.
Hello everyone, I'm Dr. Priya Hassan and I teach at the Maulana Azad University, which is in Hyderabad, India. And today I'll be talking to you about the James Webb Telescope and what's so exciting about the James Webb Telescope. Now, the telescope is in principle an infrared space telescope. So we're going to cover today, why do we want a telescope, why do we want it in space, and why do we looking for infrared? Now, the James Webb Telescope was basically the purpose of studying the universe and its origins. And the origins were to be in every phase of cosmic history, from the first luminous glows after the Big Bang, to the formation of galaxies, to stars, planets, and the evolution of our very solar system. Now, it's often called the golden eye. What you see is here you have a picture of the launch of the Space Telescope, which happened on Christmas Day. And you can see that this is an ESA satellite. This was launched from French Guiana, which is in South America. And you can see the interesting part of the telescope is you actually have a folded telescope, which you could see on top over there. And this is a typical satellite launch where you have the head, the part is where you actually have your telescope sitting. You launch the telescope. It's a multi-stage rocket where at different stages, what you do is the fuel tanks are thrown off and you ultimately the head, which is over here, which basically hosts the telescope. The telescope is sitting up over there. And you can see that this is an animation of the launch. And it's really, you can see that it's a pure engineering feat. So the first stage, you have these fuel tanks being shed off, and they fall into the ocean. It's like, all launch sites on the eastern coasts of places, so that as the Earth rotates, the thing falls in. Here's our beautiful folded telescope. You can see that these things shed off, and here you have the telescope being exposed. And like I told you, what's interesting, it's 6.4 meters, but it's folded because you could not have it launched in that form, right? So therefore, you have it in a folded form, which is put over here. And you can see that as it launches off, you have a gradual unfolding of the telescope. So here's the telescope set off on its journey. This telescope is headed towards the L2 point, which is the Lagrange 2 point. We're going to talk about it, which is 1.5 million kilometers away. It has to go that far, which would almost take a month for it to reach. And you can see that as the launch takes place, you have it happening in various stages where, first of all, you can see this takes place. And first thing you have is the solar panels have to open up. This is back. And you can see in the animation, this is the last image that one has of the James Webb. Gradually, you open up the solar panels, the first thing. And then as the telescope actually unfolds, because like I said, 6.4 meters cannot fit in an open form. So first of all, the solar panels open. This is the sun shield, which is made up of 5 layers. We're going to talk about it in more detail. And then over here, the sun shield has to open up. And only after the sun shield opens up, then you open up the telescope. So the primary mirror is over here, which is folded. And here's the secondary mirror. And you see this all has to happen with real precision so that the whole thing happens within the sequence, right? Now, telescopes, you're all aware of it. A telescope is nothing but a convex mirror, which will basically focus the light, get it to a point. It collects all the light. And you can actually observe it from your eyepiece, which then further magnifies and focuses light for your eyes. That's the basic principle of a telescope. Now, the first to use telescopes for astronomy was Galileo, who used it 400 years ago. And he actually used a very small telescope, but even that telescope was very revolutionary in the kind of results it gave, which actually got Galileo into trouble because of various reasons. Into details. The other important thing is we know the electromagnetic spectrum, which ranges from X-rays, gamma rays, all the way down to radio. And you can see that the optical window, the one that we see with our eyes, is only a very small part of the electromagnetic spectrum. And that's what we can see with our eyes. And visible light is only that. But there are various physical processes which take place, which give you emissions in different parts of the electromagnetic spectrum, which makes it necessary for us to observe in different parts of the electromagnetic spectrum. But the problem with that comes is our atmosphere. Our atmosphere is like a blanket which actually protects us from harmful radiation from the sun as well as other objects in X-rays and in gamma rays and in various other radiations. And it kind of blankets us. And because of that very reason, the atmosphere does not allow various parts of the electromagnetic spectrum to get onto us. For example, the whole of X-ray ultraviolet light is blocked. You have certain, this is the visible window. There are certain windows in the infrared and the microwave, and then the radio wave window is the largest. So what happens is that if you, for example, want to observe in different, depending on which wavelengths you would like to, you have to go out of the atmosphere. The other important problem with the atmosphere is what you can see in this window is that here I have a star and there is turbulence in the atmosphere due to which the position of the star shifts. And this is what we call twinkling, right? Which you can see in this animation. And the twinkling itself is actually a botheration for astronomers. So though twinkling is considered to be beautiful, it's actually a botheration, smudges the images of stars. And therefore we would prefer no twinkling. That means we need to have our telescopes set high up so that we have lesser amount of atmosphere and lesser amount of twinkling taking place. And that's what we astronomers call seeing, better seeing. Now, we know that there's a certain amount of seeing limitation because of diffraction, because the light itself is a wave, and therefore you have a wave pattern coming out from your source of light, due to which there's a smudging of light, right? So that is something we cannot avoid, but the atmosphere adds on to that. So if you actually go out of the atmosphere, you can, avoid that. The other important part was infrared. Why do we want infrared? Infrared, this was discovered by William Herschel around 1800, which is basically from 700 nanometers to 1 millimeter. And there are various sources which give out an infrared. We are ourselves excellent infrared emitters because our peak radiation is in that. And therefore, I would also further later on talk about why do we need infrared. But the problem is that if we want to observe in infrared, since it's an infrared telescope, we have to go out to space because that's when you will not have because these radiations will totally come in, otherwise they are blocked. We can actually achieve diffraction limited seeing. That means we will not have the effect of the atmosphere. And ground-based telescopes, they have limited observing time because of Earth's rotation, but in a space telescope, you can observe 24/7. And space telescopes could be either survey missions, that means you're observing the entire sky, or they could be in an observatory mode. The James Webb is in observatory mode. You are specifically looking at certain objects. Basically, because it's a very large telescope, the field of view is small, and therefore you cannot be scanning the whole sky. You actually look at targets which are shortlisted using certain methods. The disadvantage of space telescopes is obviously they are far more expensive than ground-based. They're difficult to maintain, specifically with James Webb, it's at a distance of 1.5 million kilometers. And therefore, if you have to do any servicing mission, it would be very difficult to do it. The Hubble Space Telescope is not very far away. It's barely at the distance of 570 kilometers. And therefore, there were various servicing missions done to the Hubble Space Telescope. But in the case of James Webb, since it's at a distance of 1.5 million kilometers, we cannot be doing that. We've already been building a whole lot of space telescopes. As you can see over here, there's Suzaku, there's Chandra, which is still operational, there's Kobe, there's Fermi. There are various telescopes. We do have a good amount of history and experience in sending space telescopes, though everyone is a newer mission. And the one that you're most aware of is, I'm sure, the Hubble Space Telescope. You can see the launch over here. And the kind of data that we've got from the Hubble Space Telescope is like mind-blowing. So the other very important space telescope, which is still in operation, is the Chandra Space Telescope. It observes in the X-ray. And there's very important physical processes, high energy processes, which take place in the X-ray. And therefore, you have to observe that with an X-ray telescope out in space. And that's what Chandra is. And I don't have the time, but there's a lot of interesting stuff which we have learned with Chandra. And I would urge you to actually have a look on the internet at some of these things. Now, the other interesting space telescope is the Spitzer telescope. Spitzer telescope observes in wavelengths from 3.6 160 microns, which is in the infrared. It's a smaller telescope. It's only less than a meter, 0.85 meters, but it has also given us some very interesting results. Herschel is also an infrared telescope, which looks at little longer wavelengths than the wavelengths which are available with Spitzer. It's a larger telescope, 3.5 meters, with very interesting results. Now, we won't go into details for Hubble. I'm going to skip it. And you can actually see that the James Webb, if you compare it with Hubble, Hubble is only 2.4 meters, this is 6.5 meters. And like I told you, since James Webb was actually meant to study the origin, we basically want to look back in time when galaxies were very young, but the universe was very young because we want to see how galaxy evolution has taken place. As well as we want to look at very far away objects, so we need a very large mirror. And the problem is if we are looking at young stars and planetary systems, there's a lot of gas and dust in there. And if you look at gas and dust, the thing is that gas and dust, it absorbs emission and then re-emits it in the infrared. So if you want to observe at objects which are gassy and dusty, you have to look in the infrared. That's when you're going to be able to see it. So if you want to see young stars and young planetary systems being forming, you have to observe it in the infrared, which is what James Webb is up to. And then if we want to look at young galaxies, we'll see why do we need to look in infrared. So people actually think that James Webb is a sequel to Hubble, but in principle, it's not. I showed you a whole range of space telescopes, and in principle, you could say that Hubble is a sequel to Herschel. It's more closer to Herschel in terms of wavelengths, or you can even say in terms of Spitzer, but it's more as a successor to Herschel because it's basically looking in the infrared bands. Now, the expertise that came into Hubble is basically in making the mirror and the sunshade. That's basically because we are looking in the infrared wavelengths. And like I mentioned, we are excellent infrared emitters. The Earth, the Sun, they're all excellent infrared emitters. So therefore, you have to protect the mirror from infrared emission. And the mirror sunshade was all done by NASA. ESA did the rocket launching as well as the MIRI instrument on it. Canada basically has excellent experience on robotic arms, on space telescope, as well as they did the camera on it. The total cost of the telescope was about 11 billion. The launch itself costed 1 billion. Now, like I mentioned, since you have this difference in sizes, the advantage you'd have would go as a d squared, right, as a square, because it is the area. And therefore, you can actually see that the ratio 6.5 divided by 2.4, you'd actually have, if you square it, you'd actually get about 7 times more collecting area. And with the size of the telescope, obviously, you'd have a much better resolution and it's like that. So if you were to compare the two, Hubble, like I mentioned, is only at a distance of 570 kilometers. The James Webb has been sent at the L2 point, which is at a distance of 1.5 million kilometers. And because the James Webb is such a large telescope, it is basically made up of segments. There are 18 segments which make up the mirror to get the final diameter of 6.5 meters. A Hubble is a single glass mirror of 2.4 meters. Like I said, James Webb is too far away to be serviced, while Hubble was serviced multiple times. And because it's an infrared telescope, it needs to be cooled, and therefore it has a finite lifetime, about 10 years, while Hubble has been on, and it's still on since the 90s, right? So it's still very this thing, because it's basically we're looking in the optical light. You do not need to have separate mechanisms to cool the telescope. Now, we'll get back to infrared. All of you all are obviously aware of Edwin Hubble and his theory of the expanding universe. So briefly, what is there is Hubble. This is Hubble observing with the Mount Wilson telescope. And what he did is he looked at the spectra of various galaxies. And using Doppler effect, he could get the velocities of these galaxies. He also studied the distances to these galaxies using a particular kind of stars called the Cepheid variables. Now, Cepheid variables have a strong correlation of period luminosity, and this is with absolute luminosity, and therefore you can actually use Cepheid variables as standard candles to actually get distances to galaxies. And that's what Hubble did, is he measured the velocities with the spectra, got the distances with the Cepheid, from the Cepheids in those galaxies, and he came out with this excellent relationship between the velocity and the distance to galaxies, which is what is called the Hubble's law, which is the velocity of the galaxy is h naught into d, where h naught is the Hubble's constant and d is the distance to the galaxy. So what he basically saw that as a galaxy's distance increases from the Milky Way, the velocity with which it moves away from it also increases. And therefore, what you see is that you actually get a feeling of there's an expansion of the universe. The galaxies further away from us are moving further away faster, and the ones closer are moving slowly. Now we go back to the Doppler effect. What is the Doppler effect? That if I have a source of light and it's moving away from me, the wavelength gets actually stretched, so it moves towards redder wavelengths, which is what we call redshifted. If it's moving towards me, it gets kind of squashed, so it moves to shorter wavelengths, which is what is called blue shifted. So what you do is you are basically measuring the delta lambda. And because there's an expansion of the universe, the wavelength, if a star was emitting in a certain wavelength, that very wavelength gets shifted to the redder part of the spectrum, which is essentially the infrared part of the spectrum. So that means if I want to look at a galaxy which is very far away, which has a very large velocity, it will have a large distance, it will have a larger velocity, it will have a larger delta lambda, and that delta lambda would be towards the infrared. So if you actually look at the spectra of these galaxies, if the galaxy is very close to us, say the spectral line is over here, and as the galaxy, you can see the redshift of the galaxy is larger, it moves towards the redder part or the infrared part of the spectrum. So if I want to look at a galaxy which is at a large redshift, say at a redshift of 6.26, I need to look at the infrared part of the spectrum so that I can look at the spectrum which was originally in optical, but it is now in the infrared. So I will need to look at it like that. So in principle, it's a time machine. When you are actually looking at large redshifts, you're looking through a time machine. You're looking at objects as they were much younger away. So if I'm looking at things which are further away in the universe, I can actually look to an earlier part of the universe. So essentially, as I go at larger redshifts, I am going to an earlier and earlier universe. So I'm going, as I go to larger redshifts, I can go back in time. That's the approximate age of the universe, and I'm going back in time. And therefore, with our various telescopes, as we've been looking deeper in the sky, we are going to earlier parts of the universe. So for example, with ground-based telescopes in the 90s, we went to about an age of the universe till it was about 6 billion years. With the Hubble Deep Field, we've gone deeper. And now with James Webb, we are going to go to an age of the universe when it was barely 200 million years old, so that we can study the origin of the universe, see what it was like when it was 200 million years old, right? And therefore, we need to look in the infrared. So the infrared is essential, number one, to look at early galaxies. If we want to look at the early universe, we need to look at earlier redshifts. At earlier redshifts, the original light would be in infrared, so we need to observe in infrared. The second thing is that if we are looking at young planetary systems, this is Orion Nebula, where you have young planetary systems forming. There's a lot of gas and dust over there, and therefore the peak of the emission is in the infrared. We have to now look in the infrared. And therefore, when you're looking at young galaxies, young universe, as well as young stars and planetary systems, we have to observe in the infrared, and therefore we are going to have to do this thing of looking in the infrared. And therefore, though Hubble Space Telescope was in the optical, James Webb had to be designed for the infrared so that we can suit this purpose about studying the origins. Now, this is the same image if you were to look at it in the optical, and here you can see it in the infrared, and you can see the amount of detail you can see. This is a star forming region. You can see the amount of detail you can see when you are actually looking in the infrared. And that is what changes the basic purpose of the James Webb and why do we need it in infrared as well as in space, right? Now, like I told you, in principle, the Webb is a Herschel complementary because Herschel looks in similar wavelengths as James Webb does, okay, which is 55 to 670. This is even longer, while the Webb is looking basically from 0.6 to 28.5 micrometers. So the overlap is more with Herschel than it is with the Hubble space. Now, like I mentioned, is that because this telescope is an older telescope, you can see that a very important part is about aligning the mirrors because you are actually using 18 segments to together give you the effect of a single mirror, right? And therefore, what you actually have is this is the mirror when it's being built. You can see it over here. And you can see is that all these parts have to be together smoothen up and give you the effect of a single mirror, right? And therefore, what you have is each segment has a size of 1.32 meters. And together they add on to give you a single primary mirror, which has a size of 6.4 meters, right? And therefore, here you can see is you can see that it's like you can see in this, it's a perfect engineering feat of how they actually built the whole telescope to give you this. The secondary mirrors over here, which has a size of only about 1.74 meters, which is over here. And this is your primary mirror with all the segments. Now the segments have a base with their accentuators. These are the support for the mirrors. And the support has to be made in such a way that when we add up all these segments, all the 18 segments, these are all the segments put together, they have to, in principle, be aligned to a fraction of the wavelength of light, right? So that together these 18 segments will give you the effect of a single mirror, right? And therefore, that was a very important step in the launch of the telescope, that after the telescope was launched, each mirror would give a different image, but you had to align them, right? This took almost a month, 3 months to align all these mirrors so that all of them give you the image at the same focal point, right? So this was a very torturous process of actually aligning this. So you have these accentuators, sensors below each mirror, which will help to align the mirrors so that you get it all together, right? And that's the kind of job which is done when they did the alignment of the mirror in the initial stages of the telescope, okay? Which was a very important stage and a difficult stage. So like I told you, you have primary mirror segments, you have secondary mirrors, there are tertiary mirrors, fine steering mirrors. If you look at the path of light, the light comes in, the light beam comes in onto the primary mirror, and then the primary mirror focuses it on the secondary mirror, which is over here. And then from the secondary mirror, it gets bounced off, and here it goes to tertiary mirror, from which it is then redirected to the various instruments which are there on the telescope. Now, the sun shield, like I told you, is a very important component of this thing, because we have to protect the telescope from any kind of radiation coming from the Earth as well as the sun or anything else. And it's made up of 5 layers. It's made up of a specific material called DuPont, which is membranes which are specially coated with aluminum on both sides and a layer of doped silicon. And these ones are very fine structures which are made up in 5 layers. It's the size of a tennis court, and it will protect the mirror from all kinds of radiation. And this has been a very important part of the construction of the telescope. And after the launch, it had to basically open up before the mirror opened up so that it could protect the mirror from all these radiations, right? And right. Now, where is the James Webb located? It has to be protected. And therefore, there are 5 Lagrange points where the gravitational force between the Earth and the sun is balanced. So L1 is the one which always faces the sun, but L2 is over here. It will never face the sun. You'll always have the Earth between. And James Webb is basically at the L2 point. So you can see that as the Earth goes around the sun, this one, the telescope is behind over there. It will always be behind. So you could always find the position of the Webb. Webb is always in the opposite direction of the sun. So if you look at the crescent moon, this is the direction of the sun. This is the direction at which you have James Webb. Right? Now the instruments on the telescope are, there's a near infrared camera, there's a mid infrared instrument, and a fine guidance support. And all these have been developed by different teams, and it's an engineering wonder beyond doubt. So you can actually see the way everything has been built. It's really very beautiful. The way it was all built together, packaged together, and put it together. And all this was done at the Goddard Space Center near Washington, D.C. You can see all the components were put together. It was literally packed up. And you have secondary mirror over here. It all has to be beautifully folded and all that. And it was packed up and actually put onto a barge with which it actually had a long trip, with which it went to French Guiana. Right? So you can see this is the barge. You can have a look at the barge. So you had the complete testing. It went on its barge, where it did a 16-day journey to actually reach South America, Uru River, where you had the launch. So when you had the launch taking place, you had the separation, which I showed you, the sun shield open off, the telescopes open off, and then it gradually reached the L2 point, which took it a month. And so before it reached L2, it had to go through all these steps. We won't go to this, so you can actually see the way it was deployed. We skip this. Okay, so we'll skip this, and we'll go ahead. This was the last view we had of the James Webb. And the first images we got were obviously like this, because each segment gave you a different image, which I told you. So you had to align every segment so that they give you the mirror alignment, which took a long time, about 3 months to actually align it. Now, the early science programs would obviously look at stars, look at exoplanets, look at galaxies, look at dark matter, look at various features. And the first images were out in July. The launch was on Christmas Day in 2021. And then within 7 months, you had this was the first image, which was given out by the president, by Biden. And this is basically of a galaxy cluster where you can see beautiful images of gravitational lensing. And this is the S-mass cluster. And you can see that these are the redshift mark of the kind of objects we are looking in. So you're seeing we are really looking very, 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 very back in the universe with this thing. They are a perfect example of gravitational lenses. You know that gravity can work like a lens and it can bend light and actually give you lensed images of this kind. What people noticed in this gravitational thing that they actually saw disks being formed at galaxies at a very young age at redshifts greater than 3. There were papers already out. This was out within a week of the data being out of the morphological estimates of galaxies, which were done with that image. So this is the first paper which was out, which was using galaxy structures, very interesting one. There was an oldest galaxy also observed from this, which had a redshift of Hourglass Z13, redshift of 13. And there are various other baby galaxies that have been observed in that image. We also observed the Stephens Quintet, which is a visual grouping of 5 galaxies, of which 4 are gravitationally distinct. You can actually see them. All the instruments were used to actually get spectra of it, and we don't have the time, but they actually got the velocities of these spiral structures using various spectroscopic techniques. We can do this in a different thing, as well as the AGN in the Stephens Quintet, using various instruments. Also, they observed, this is the Southern Ring Nebula, which is basically a star in the later stage. It actually throws out its outermost envelope. This is the outermost envelope. And what you could see is in the center. Now, earlier, this was a very interesting object. This is an earlier object here. You have the James Webb object. Now, what was interesting is that earlier when people saw this, by theory of stellar evolution, as the star evolves, it will actually throw out this outer thing in the form of Lamprey Nebula. You'll have a white dwarf over here. But the problem is the central star, which we could see with Hubble, was not a white dwarf. It was a main sequence star. And now when we actually used the James Webb, we actually found 2 stars which were in there. One was the main sequence star, and the other one was the white dwarf, which was this thing of the Southern Ring Nebula. It was actually caused by this. So the whole confusion as to how did you have this planetary nebula and you have a main sequence star sitting on the center, it was resolved by James Webb because you finally found the white dwarf which was sitting on the center, which was not so bright, and hence we could not observe it earlier. But now we can see it. We also saw, we have that. Even, there were interesting things like even in this very image, there was a galaxy over here, and people observed this galaxy and they found some very interesting results over there. This is of a distant spiral. There's a star-forming region called the Carina Nebula, which was also observed by the James Webb. There were basically 5 early images. It's a star-forming region. You can see it's beautiful. The kind of difference of the kind of image which we could actually see. I will not go into this, but the Carina Nebula is a region of star formation. It's not very well observed by the Hubble Space Telescope because there's lots of gas and dust in there. But now when we look with James Webb, we can see it very well. You can see jets coming from young stars. You can see young sources. You can actually see the kind of star formation taking place over there. Another interesting thing which was done with James Webb was an observation of an exoplanet. This is an exoplanet for which you have a transit light curve. This is not what James Webb did. We know this is the light curve with which we know that you actually have an exoplanet over there. What James Webb did is it actually looked at the spectra of this exoplanet, WASP 96P, and it actually found it and found water molecules. So it actually showed its capability of studying the atmospheres of exoplanets. And therefore, this was just the beginning of the initial images with James Webb. There are already many more images pouring in with the James Webb telescope. And you can actually have a look at them on the net from the near infrared camera, from the MIRI instrument. They are very nice instruments available. There's images of Jupiter, which actually showed you its equatorial zone and the red spot, as well as, these aurora on the poles and various other, satellites which were observed with it. There are, I would like to wind up with this, with a few memes on James Webb, that here is a comparison of the Hubble Space Telescope and the James Webb of the kind of difference in which we are actually getting images. Most of you all would be aware of Spider-Man, and that's what Spider-Man could see with Hubble, and this is what Spider-Man now sees with James Webb. So you can actually see that there's a lot of exciting science we are going to get with James Webb, and that's what we are all looking forward to. Since it's a short talk, I do not have time, but I would encourage you to have a look at the net and see all the kind of, data we are getting in. But I would obviously tell you that if this is what Hubble gave, this is not what James Webb is going to give. But James Webb is definitely going to give us very interesting results, which we are all looking forward to. So keep having a view at the news, which is there on the net, and you'd see a lot of this thing. The future, NASA is also going to have a Nancy Grain Roman telescope in 2027, and probably a Super Hubble, which would also be there to actually this thing.
Register now on bit.ly/Intro2Astro 2024.